Hey y'all, my goal for this video is for you to optimize your AB, BC calculus exam score. I'd love for you to benefit from my 15 years of teaching and grading the AP exam. If you find this video helpful, I'd love for you to like, subscribe, or leave a comment down below. I'm going to be going over the most essential elements of the AP calculus curriculum, many of which you see on the review sheet on the screen in front of you. This review sheet has all the things you need in order to be successful on the AP exam, distilled down to about 8 pages. If you'd like to purchase a copy for $3, look down in the comment section below to see how to do that. With no further ado, let's get to it. BC Calculus has a couple different integration techniques that you'll need to know. Integration by parts is one of them. It involves this formula. This is the integral of u dv equals uv minus the integral of v du. Typically what's going to happen in some sort of integration by parts formula, it's going to be kind of like the product rule for integration. You're going to have like the one below where you see you have x squared sine of x. You can't do a u substitution because the derivative of the inside function is not x squared, and so it won't be a u substitution. You basically have a product rule right here. And so what you're going to have to do is you pick one side, one of these, to integrate in one of those parts to take the derivative of. And typically you're going to take the derivative of the polynomial or monomial portion because its derivative is eventually going to go to 0 after you take a few derivatives. And then you pick the other side as something you can integrate. And don't forget to use your simple u substitutions to get those coefficients. Now, when we do the tabular method for integration by parts, you take the derivative like this in the table, you integrate the other part like so, and then you're going to put plus, minus, plus, and when you get to 0, you don't really need to. And then just draw arrows down like this. Okay, and then that's going to be your integral. So it's going to be x squared times negative 1/3 cosine of x, and that gives you that first term. You're going to say negative 2x times negative 1/9 sine of 3x, that gives you the second term, and you do that all the way down. Now, once you get to 0, you don't need to go past the 0 because 0 times anything equals 0, and then you're done. The second technique is going to be this integration by partial fraction decomposition. So you're going to recognize this one whenever you have something in the denominator that factors. Typically it's going to be a quadratic that'll factor, or maybe it'll be factored for you. But you're going to have to be able to split this because typically on these you're not going to be able to do a u substitution because the derivative of the inside function or the denominator will not equal the numerator. And so when we split this into partial fractions, a little bit of an algebra technique maybe you learned in pre-calculus. That does this, and then each one of these parts can be integrated much simpler, right? And typically they're going to be these natural log antiderivatives. Now, you might be saying, how did you get the 2 and the 4? Well, that's just doing this algebra where on this one we multiply both sides of this equation by x plus 1, x plus 2, and when you do so, the denominators are going to cancel out, and then the x plus 1 will cancel out, and you'll be left with, a x plus 2 and b x plus 1. So you end up with this equation right here. Now, we're going to try to figure out what a and b are. Well, a is going to end up, what we do is we're going to plug in x equals negative 2. When you do that, this first term with the a in it is going to be 0, and you'll be able to solve for that b value. Then you're going to make x equal negative 1, which is going to end up turning the second term, this b term, into 0, and you'll be able to solve for a. And once you do that, you'll have a much simpler integral to solve, and you'll be able to take the antiderivative of that. In BC Calculus, we're going to have to deal with two-dimensional motion, or parametric in vector motion. Typically what's going to happen is your x-coordinate and your y-coordinate are going to be defined separately in terms of time. Now, if you can do one-dimensional motion, it's really not that much different. It's really going to be almost the same thing. Your dx dt is going to be your rate at which your horizontal coordinate is changing with respect to time, which will be your horizontal velocity. Your dy dt is going to end up being your vertical velocity. And if you want to write the velocity vector, you're just going to write them just like almost like a coordinate point like this with these little symbols right here that signify that we are writing a vector. And so you have your horizontal component and your vertical component. Same likewise, your second derivative with respect to time is going to be your acceleration vector. And you're going to do the same thing. You're going to basically keep your horizontal and your vertical components of your acceleration separate. Now, if you need to find the slope of the tangent line to the curve, well, that's going to be your dy dx. So notice this is dy dx, which is not dx dt and dy dt. You're getting rid of the dt's completely. And the way we do that, you can see down here, I kind of have it out of order here, your dy dx is really going to be your dy dt divided by your dx dt. And you can imagine if you do the little fraction math and multiply by the reciprocal, the dt's are going to cancel out. Now the big change with the two-dimensional motion is going to be finding the speed. In one-dimensional motion, the speed is just the absolute value of the velocity. Well, it's the same thing here. It is the magnitude of your velocity vector. Well, what you're going to have to do to find that is you're going to have to take your horizontal component of your velocity and the vertical component of your velocity, and then you're going to add those together. And with vector addition, it's just going to end up being the Pythagorean theorem to find that magnitude. So that's all it is. It's just your dx dt squared plus your dy dt squared, take the square root. It's just the Pythagorean theorem. And then likewise, to find the total distance traveled, well, your total distance traveled is speed times time. Well, the issue there is that speed is changing constantly. So in order to account for that, what we're going to do is use an integral. An integral doesn't matter whether the speed is changing. That's why we have integrals in the first place. So if we want to find the total distance traveled or the length of a parametric curve, all we do is we take that speed function we just have and we integrate that from, t equals a to t equals b. Now, if we want to find the position, final position, well, we're going to do those separately. We're going to find the x position separately, just like we did in one-dimensional motion, where we take our initial position plus our displacement in the horizontal direction. That's what that integral means. And that's going to end up finding our final position b. We do the same thing with y, our initial position plus our vertical displacement, and that's going to find our position in the y direction. Now, also, we're going to end up having to do polars. Typically, one of your FRQs is going to be either a two-dimensional motion question or a polar motion. Sometimes the polar motion is really just a parametric motion question disguised, because it gives you a polar equation, but really it wants you to change the polar equation into its x and y components. All you have to do is take that polar equation and then multiply it times cosine theta to get the x coordinate, and then times sine theta to get the y coordinate. And if you're going to go ahead and find the slope of the tangent line, you would just take the derivative of each of those and put them over each other and get dy d theta over dx d theta. I mean, you can memorize this right here, but really it's just going to turn into a product rule of the derivative of x and the derivative of y, or rather dy d theta over dx d theta. Now, the big thing with polar is they're going to want you to be able to find the area of a polar region. And that's real easy. The thing is, you just have to memorize this formula, and it's basically instead of where we did a regular integral to find area, we add up an infinite number of rectangles. What we're doing here is we're adding up an infinite number of sectors, and a sector is 1/2 r d theta, or r squared d theta. That's really what the little infinitely thin sector is going to be. And so you just have to know that formula. It's going to go from theta equals 0 all the way to theta equals, beta, or whatever you want. And so just kind of imagine, like on the unit circle, you're traveling around you're radiating out sectors from the origin out to the curve from, angles on the unit circle going forward from, A to B. And that's really kind of all you'd have to do. Now, occasionally you might have to find the area between two curves, and really, you could do this in two separate ones. You could actually find the area to the inner curve and then subtract out, the area to the outer curve and then subtract out the inner. But keep in mind how these areas are formed. If you have, they're basically all these sectors radiating out from the origin. So you have to think about it in that way. That's how you're piecing them together. And so you're just doing it from this angle here, from angle theta, all the way around to whatever your final angle is. And it will actually calculate those area by just radiating out sectors out to that curve. So it's important that you understand how they find those values on that polar curve. But ultimately, your formula is going to end up being this 1 half, from theta equals A to theta equals B of r squared d theta. You're going to need to know logistic growth as well. Logistic growth shows population growth, but with more of a realistic tinge than exponential growth. It's where the population growth rate is proportional to both the population itself and the difference between the carrying capacity and the population. So you're going to see a differential equation that looks like this, where C is the carrying capacity, which means the maximum, the logistic growth curve can be. So you'll see it'll look kind of like this S curve right here, right? And so the graph is actually going to end up producing like this horizontal asymptote as the graph gets closer to the carrying capacity C. Now, a couple important things to note on here is that at 1 half C, you're going to have a spot where there's going to be a point of inflection, and that's the spot where the population is growing the fastest right there. And so you have to kind of know that. The other thing is these limits are very common that you see down here, where it tells us what is the limit as t approaches infinity of p of t. Well, that's going to approach that carrying capacity c. So that's going to be the limit of the population is going to be that carrying capacity. And then it's going to ask you, what is the, as t approaches infinity, what is the derivative of that population going to be? Well, as you can see, the slope of the tangent line has a horizontal tangent line. It's going to end up approaching 0. Now, what's hard about this is there's no t's in this differential equation. They're going to ask you some limits as t approaches infinity, and you just kind of have to recognize that this is a logistic growth, and this is how the curve is always going to look. The next thing you're going to have to do, sometimes in the same question because it's going to have a differential equation, is Euler's method. Euler's method is kind of a repeated tangent line approximation. And so what it is basically this, right? You have y is going to equal, this is like your dy dx right here. That's really what this is, dy dx, your derivative. And then you're multiplying times delta x plus your initial starting value. So it's really just like a tangent line approximation. And so all we're doing here is we're taking our, we're going to be given some initial point and asked to approximate someplace else with, 2 steps of equal width. So we know each step is going to be a delta x of 0.5. So we're going to take our derivative, and that's going to be our slope that we're going to apply for a step of 0.5 units in the x direction. Notice whenever you multiply, delta y over delta x, which is slope times delta x, that just gives you a change in y. And that's really all that's happening here. And we're adding that change in y to our original y. And so that's really what's going on. So we have this slope times 0.5 plus our initial value, and that's what it looks like over here. So if we were to plug in 1 and 3 into our derivative right there, you're going to get a slope of 5. So we just 5 times 0.5 plus 3, and we get 5.5. And now we have a new point, and we're going to update our slope. So our slope now, we're going to take the slope when we use 1.5 and 5.5. And so we do that, and we get a new slope. In this case, we're going to get a slope of 8.5. Again, our delta x is not going to change. It's going to be 0.5 plus our last value, the value we just found, right? We're going to be adding to that, and we end up getting our final approximation using Euler's method. Series convergence can be one of the more abstract ideas on the AP exam, but the reality is once you wrap your mind around it a little bit, there's some of the easiest questions on the AP exam. The way I tackle it is I'm looking at a series, like for example, you'll have some sort of series from n to 1. It could be anything from 1 to infinity of a sub n. We're going to add up an infinite number of numbers. And I think to myself, if I'm going to add up an infinite number of numbers and I'm expecting it to converge to a finite value, those terms better be going to 0. So that's the first thing I look at. I look at what we call the nth test for divergence. If the limit as n approaches infinity, if those terms are not going to 0, then it definitely diverges. Now, the fact that the terms do go to 0, if they do, that doesn't tell us whether the series converges or not. So you can never use this nth term test to tell about convergence. But if it passes the nth term test, let's move on and let's start looking at other ways to see if this series converge. The next thing I look at is, does the series alternate, right? Alternating series are also pretty easy to determine whether they converge or diverge. If you have an alternating series, you'll usually see an alternator like this, -1 to the n or -1 to the n plus 1. And typically what you're going to be looking for is, does this series decrease in absolute value to 0? If so, it converges. That's it, right? So if we look at this series right here that we're looking at right there, if we take -1 to the n over n, if we just had 1 over n, that series would not actually converge. But the fact that we have an alternator on it, the series will converge because these terms do go to 0, right? As n gets larger and larger, we're going to start dividing by bigger and bigger numbers, meaning our answers getting smaller and smaller are going to go to 0. Thus, this will be a converging alternating series, and we'd say converges by the alternating series test, or you can just write AST. If it's not alternating, we're going to look for a series, a p-series or a geometric series to compare it to, right? And so for p-series, we found that the breaking point of a p-series is right at 1 over n. So the series are going to converge if that p-value right here in this p-series, oops, let me put this right here, excuse me, put that p-value right there. If that p-value is greater than 1, the series is going to converge. And hopefully that makes sense, because the bigger that p-value is, the smaller the terms are going to be, because the larger that denominator will be. If you have a really large denominator, you're going to be dividing by a much bigger number, making the terms of this series get really, really small. Now, if that p-value is not big, which means less than 1 or equal to 1, our series is going to diverge because the denominator won't be as big. It'll be a little smaller. Right? And so typically what we're going to do is we're going to try to compare a series. So you might look at something like this, and it doesn't have, there's no p, it's not really a p series, but what we can do is we can take the highest degree terms and we can compare those, right? And so we compare the n squared over n cubed and say it compares to 1 over n. What you do not want to do, you do not want to sit here and cancel those out. That is terrible algebra. I see that all the time from when I grade AP exams, that students do things like that. That is terrible. You're just going to compare the highest degree terms and compare it to that. And you realize 1 over n, that's a diverging series. So therefore, this series right here diverges. Also, likewise, we're going to look at this series down here, and we can see that if we were to subtract those exponents, we're really going to compare it to 1 over n to the 3 halves. And that is greater, that p-value right here is greater than 1, so therefore our series converges. Now, if we see that we have a geometric series, geometric is going to look like exponential functions. So you'll have something like this, where you have like 2 times 1/3 to the n, or something along these lines, where you've got some sort of exponential function where this exponential base is the common ratio. That is what we're multiplying each time to get the next term. If that number, if the absolute value of that number is less than 1, then that series converges, right? And that's the only way that series converges. And you can imagine if this value right here was bigger than 1, the terms would be getting bigger and bigger, and then it wouldn't even pass this nth term test for divergence, right? And so that's really all we're looking for. Now, if none of those are the case, we may have to use the ratio test. The ratio test is typically used when you've got a mix of factorials, exponentials, polynomials, kind of all mixed together. And what we're going to do in this case is kind of like a geometric. We're going to go ahead and find the common ratio between terms. We're taking the n plus 1 term divided by the nth term, or any term divided by its previous term as n goes to infinity. So we're looking at the tail end of this series and determining, are we multiplying by a number greater than 1 to get the next term, or a number less than 1 when we talk about the absolute value? And if it's less than 1, just like a geometric, it's going to converge. If the common ratio, when you take the n plus 1 term divided by the n term, is greater than 1, then that series will diverge. Now, if it equals 1, it's inconclusive now, because we're talking about a limit. And so these things didn't actually equal 1. It just approached equal 1. Well, you could approach 1 from either side. So that, it's inconclusive when the ratio equals 1. Now here's a little example of when we're dealing with the ratio test. You might have something like this, a mix of, we got exponentials, factorials, and a monomial in there. Well, you're going to take the n plus 1 term, so all the n's are just going to become n plus 1, and then we're going to divide it by the nth term. When we divide, it's the same as multiplying by the reciprocal. So we're multiplying by the reciprocal of the original. Now, when we do this, I always like to, split this out so I can cancel things out. So realize that 6 to the n plus 1 is really 6 times 6 to the n. And that makes it real easy to reduce. right? Now, if I'm going to, and same thing with n plus 1 factorial. That's the same as n plus 1 times n factorial. And so those would cancel. Now, the other thing you have to make note of is these polynomials. They're gonna end up equaling 1 because the limit as if n plus 1 squared over n squared, that equals 1 because really the n squareds are the only thing that really are the only significant terms as n goes to infinity. We're going to dominate the numerator and denominator, right? And so it's like if you had a billion 1 divided by a billion, it's going to be essentially 1. That plus 1 really isn't going to matter much. So you're going to reduce this out, and what you're going to end up with after you apply this limit, apply the limit that these are going to go away, the n factorials are going to go away, and the 6 to the n is going to reduce out. All we're going to be left with is 6 over n plus 1. Now we apply this limit as n approaches infinity. Well, we have 6 divided by infinity, which is going to approach 0, which is less than 1. Therefore, this series converges. Now, oftentimes we're going to have to use this ratio test to find what we call an interval of convergence. And what this is for is these are for power series. A power series is a series where you have actually a variable in there. And for certain values of x, this series will converge. Well, we need to find out on what interval this series is convergent. And so what we're going to do is we're going to use the ratio test, and we're going to actually solve this ratio test for where the ratio test is less than 1. All right, so all I'm going to do if I'm going to find the interval of convergence of this series right here, I'm going to take the n plus 1 term over the nth term. And so again, multiply by the reciprocal. And so I'm going to do the same thing. I'm going to simplify it the same way I did where I took, x to the n plus 1 is really x times x to the n. And that allows me to reduce out these x to the n's. As well, likewise, again, we have this idea that the limit as n approaches infinity of n over n plus 1, that's just going to equal 1. So these n and n plus 1, that's just going to be 1. And then again, you have this n, the 2 to the n and the 2 to the n are going to cancel out. All we're going to be left with is this absolute value of x over 2 is less than 1. So we just have to solve that equation, which is quite easy because really for this to be true, the x plus 2 has to be between -1 and 1. And all we do is multiply by 2 on through this inequality, and we end up getting the interior of this interval of convergence, which is -2 to 2. Now, the important part is we're going to actually have to test the endpoints because the endpoints do not have to be the same on either end. And so we're going to actually just plug in -2 back into the original series and realize that when you plug in -2 to the n, that is the same thing as -1 to the n times 2 to the n. And so those 2 to the n's cancel out. And so we realize this is going to be an alternating series, -1 to the n over n, which converges by the alternating series test. So at -2, the series converges. But if we plug in 2 into here, we're going to end up just getting the series 1 over n, which is a diverging p-series. So at the 2 end, we're going to just not diverge it, so we're not going to put equals to. And at the -2, it is going to converge at -2. And so this would be our interval of convergence. When dealing with Taylor and Maclaurin series, it is going to be essential that you memorize these 6 formulas. The Maclaurin series for e to the x, sine of x, cosine of x, 1 over 1 minus x, which is the geometric power series. And this one has actually an interval of convergence for x. The absolute value of x has to be less than 1 for this to even apply. You also need to know the Taylor polynomial centered at 0, or the Maclaurin polynomial. And you're going to have to also know that same Taylor polynomial centered at C. These are musts. If you do not have these memorized, you are going to miss a lot of multiple choice questions and the series question that probably will deal with these. And it's going to save you a lot of time. If you're one of these that can derive these formulas, they're not hard to derive, but they also will take you a lot of time. The thing I think about whenever I'm memorizing the sine and cosine is I just think, cosine of 0 is 1. And if I were to plug 1 into this, I know it's got to start with 1. Okay, whereas sine of 0 is 0, I know it's going to start with x so that I end up getting 0 when I plug in 0. And that's how I remember which one is which. And then, cosine is all the even ones, sine's all the odd ones. The nice thing is they're pretty easy to memorize because everything is very matchy-matchy in the formulas. Now, as far as manipulating the Maclaurin series, if you are ever doing, quotient rule upon quotient rule and product rules upon quotient rules and all that kind of stuff to try to get a Taylor polynomial for some function, you're probably doing it wrong. Typically what's going to happen is you're just going to want to manipulate, if they're asking you to find, the Maclaurin series or a Taylor polynomial for x sine, x cubed, it's not asking you to find the first 7 derivatives of this f of x. That's going to be way hard. Okay, what you really want you to do, it's really wanting you to write out the Taylor polynomial or the Maclaurin series for sine, and then substitute in the x cubed for all the x's, and so all the x's just get replaced with x cubed. That means you have x cubed minus, and then you have x cubed cubed, which gives you that x to the 9th, x cubed to the 5th power, which gives you x to the 15th, so forth and so on. Okay, and realize when you manipulate the general term, if you have this x cubed, you can imagine x cubed. Ooh, that's terrible handwriting. Sorry, people. X cubed times 2n plus 1, realize you do a power of a power, and that's why you end up getting x to the 6n plus 3. And so it's just real easy to manipulate those. Now, the question I have some of my students ask me, do I do the x first or the x cubed first? Well, you want to do the x cubed plugged in first, because then if we were to distribute, if we did the x first, we would be plugging in the x cubed into both x's. We don't want to do that. We only want to plug it into that first x. So then we're going to multiply this x here second, and we just distribute x to both sides of this equation. And when I distribute x, all the power is just going to go up by 1, which then makes the general term real easy. We just add 1 to our general term exponent for x. Now, oftentimes with these Maclaurin series, there's going to be some sort of error bound we want, because obviously if we're going to evaluate x sine x cubed, we're not going to use an infinite number of numbers. No, we don't have time to add those up. So you're going to get a question that's going to say something like, use the first 3 non-zero terms of the Maclaurin series for f of 1 to approximate, f of 1, right? And so we do that. If we plug it in 1 into the first 3 terms of this series, we end up getting this right here, which equals 101 over 120. Now, if we want to know how good of approximation this is, well, remember, this is an alternating series, and so our alternating series error bound is, it's going to tell us that we are within whatever the first unused term is. Well, that first unused term is going to be 1. When x is 1, it's going to be 1 over 7 factorial. So we know the difference between the actual value of f of 1 and our Taylor, or in this case, our 16th degree Taylor polynomial, right? Or the first 3 terms of the series. It's going to be within whatever the first unused term, which was the 4th term of that series. And so it's going to be within 1 over 7 factorial. The other error bound you're going to have to know is the Lagrange error bound. Now that one's a little trickier. It has this formula right here, where it basically, if we're going to use an nth degree Taylor polynomial, the maximum error, or the error bound, is going to end up being the maximum value of the n plus 1 derivative on the interval between where you're approximating and the center of convergence, and times divided by n plus 1 factorial times the difference between where you're approximating and the center of convergence to the n plus 1 power. So let's look at an example. I know I was kind of fumbling through that there for a second, but let's take a look at this example. It'll be easier to see. If we're going to use let f of x be a 5th degree, let f of x be a function with 5 derivatives on the interval from 2 to 3, and assume that typically what's going to happen is this m value, that maximum value of the n plus 1 derivative, it's typically going to be just given to you like this in a problem. Or if you have information about the n plus 1 derivative, that's probably your m value. Okay, they don't usually make you hunt too much for that m value. And so it says, if a 4th degree Taylor polynomial for f at c equals 2 is used to approximate f of 3, determine the error bound for the 4th degree Taylor polynomial at 3, and show that it is within 1/500. So when they ask you to show something is within a certain amount, they're looking for you to use this proper error-bound form, right? So we're saying the difference between the actual value of f of the function at 3 and our fourth degree Taylor polynomial, realize in this problem that our n equals 4, so all the values in the formula are going to end up being 5. We're going to be looking at the maximum value of the fifth derivative over 5 factorial times how far away from the center of convergence that we're going to be approximating to the fifth power. So in this case, we have our m value, which we said was over here, this value over here, which is 0.2. We said n equals 4, so we have 5 factorial. And then the distance that we're approximating from our center of convergence, we're approximating at 3, our center was at 2, so it's really just going to be 1 to the fifth power. And so we would multiply this. 0.2 is really 1/5. So we have 1/5 times 5 factorial, or 1 over 5 factorial, which is going to end up being 1/600th, which is less than 500. And that's how you would prove that it is within 1/500th of the actual value. We may not know what f of 3 is, but we know about how accurate our approximation is. Thanks for watching this video. I hope you found it useful. If you like what you saw here, please like, subscribe, or leave a comment down below. Again, if you want to purchase this review sheet that I went over, you can do that. Look down in the comment section to find out how you can do that for $3. Thanks so much. Good luck on the AP exam, y'all.